as I say, the physicists now are not as dogmatic as they used to be, but they don't bother to try to really have a clear picture. So they can say, oh, but maybe it's many words, that's all, maybe this, maybe that. You see, and because they don't think it's true, the students don't know. You see, I think I say in my book that there should be at least three things that should be said. One is that there is a problem with quantum mechanics. It's not clear what it means. That's the minimum that you should do. The second thing is non-locality, because that's a theorem, okay? It's not, I mean, it's not something which you can speculate about. And then explain that Bohm is a solution. Now, of course, people will say, oh, we don't like Bohm. Okay, you don't like Bohm, fine, but what do you like? I mean, well, I was in an environment where really nobody would explain anything to me. What people were saying is that Bell had shown that hidden variable theories were impossible, which is a frequent, as you know, a frequent misconception of what Bell really showed. But that's what I heard, so I thought I was a bit lost, and I was even more lost in particle physics because it was very formal. So I turned to statistical mechanics, and I did my thesis there, and then I worked on that. And I was always interested in quantum mechanics as a hobby. I was in Rutgers, and then I talked to Shelley Goldstein and other people. And then over the years, I learned Bohmian, what is called Bohmian mechanics, and what I call the Bricmont theory. And that's how I wrote my book, Making Sense of Quantum Mechanics, you see. I gave a talk explaining, I mean, at the end I said, well, I think it's a minority, it's a growing minority. Of course, all minorities tend to say that. But I think it's true. But, physicists, I mean, I was discussing with a friend, and he says physicists are all over the place now. There is no, I mean, people are not that gung-ho about the orthodoxy, you see. Again, when I was a student, there was a professor who said Bohr has explained everything. He refused to explain how, but there was an extreme dogmatism, you see, extreme dogmatism. Bohr better shown that there are no hidden variable, and quantum mechanics is complete, and Bohr explained everything. It was really very painful, and that was the generation, if you wish, that came after the founding fathers. Okay? So I'm talking about being a student in the late 60s, early 70s, and the generation there, they'd been really, absolutely convinced in the 50s when they were students, 40s, that everything has been solved by the founding father. By that they meant, of course, Bohr, Heisenberg, Pauli, etc. Okay, von Neumann, and Einstein and Schrödinger. Their objection were misunderstood. I mean, Einstein, the EPR paper has never been understood by them, and it wasn't understood by Bohr. So it was quite, and now I think the dogmatism is over. Not with these people from that generation are still alive, haven't changed their mind, but and some do. I mean, actually, one of my professors was reading my book, and he was like over 90-year-old. So, I mean, but you see, but then the younger generation, they may like many worlds, or they may like spontaneous collapse, or they may like, I don't know, the relation interpretation, or maybe what truth does, and so on and so forth. And they don't think it true, and there's you have this impression now that it's almost like a postmodern world, that you have a myriad of interpretations, and then they'll say, oh yeah, maybe there are all these interpretations, maybe Copenhagen needs to be fixed, or maybe something like that. It's not really shut up and calculate, but just that there is no clear idea about what to think. And I of course in my book I advocate Bohm and only Bohm. I mean, I don't think there's really any competing idea about valid competing idea about quantum mechanics. But it's true that Bohr. I mean, it's very interesting that I gave a lecture in February in Belgium but in French, about the Bohr-Einstein debate, and I tried to show that really, if you look at the debate, Bohr in 27, in 35, the Solvay Congress, in 35 with the EPR paper, and in 49 when there was this, Einstein philosopher scientist series of paper, you see that Bohr never understand the fact that what bothered Einstein in quantum mechanics was that it is non-local. Because he thought that this non-locality is artificial. He didn't know about Bell, and Bell came, like many years after his death. So he couldn't think even. I mean, in fact, he didn't like Bohm's theory or the Breuil's theory because it was non-local. That's what bothered him. But ordinary quantum mechanics was non-local in ways that was never clear to Bohr. And if you take a strict instrumentalist viewpoint, which I'm not sure Bohr did, I'm not sure what Bohr really thought, but, it's sort of very difficult to figure it out. But there is this, you know, he doesn't understand what Einstein means. And Bohr, nor does Bohr, by the way. I think Bohr had the following view, that we cannot talk meaningfully about the microscopic world. We can only talk about our interactions with the microscopic world, but you cannot describe the microscopic world as it is, the thing in itself, to take the title of the podcast, as it is, independently of our measuring devices. So it's not that he's instrumentalist in the sense that he would be happy about it, but he just thinks that that's what the lesson of quantum mechanics. You just can't talk about the microscopic world. And you cannot say, for example, that particles, we don't know the position and the velocity of a particle at the same time. Many people make a big fuss out of it, but I don't understand why that would be surprising. I mean, why should we know everything? And of course, if you you have to measure a microscopic object, then you will perturb it. What's unnatural about that? What is so surprising about Heisenberg uncertainty? But what he meant, and I think Heisenberg did not mean it like that, what he meant is that they're not uncertainty, but undetermination, so that there is no position and velocity before you measure. And in that sense, it's not that you choose to be an instrumentalist, you are forced to be because of the nature of quantum mechanics. That's how I understand Bohr. EPR is what I call the EPR dilemma. I mean, of course, they didn't pose it as a dilemma, but either, the world is non-local or quantum mechanics is not complete. You must add hidden variable because it's very simple. You have this perfect correlation at a distance. So you measure something here and you can tell in advance, then you can tell what will be the result of a measurement over there. If there's no action at a distance, measuring here cannot possibly perturb the physical situation over there. And therefore, the property that you're going to measure must pre-exist to the measurement. It's as simple as that. I don't understand why people miss it. Of course, it wasn't maximally explained because Modin remarks that you don't need to have both position and momenta. You just choose one of the two, or you just do position measurement, and then you know the position on the other side. But if the position on the other side didn't exist before the measurement, as for example Bohr would think, then how come that it exists after the measurement far away, if there is no action at the distance? It's just as simple as that. But obviously people misunderstood it, and it's, the answer of Bohr to EPR was dissected very cleverly by Bell in his book. I mean, he takes the passage and he says, what does it mean? And then he says, well, maybe what it means is that Bohr actually, concedes action at a distance, but not clearly. And in fact, because of relativity, and because if people had said that clearly back then, that would have been a revolution. In fact, when Bell proved, the second step is Bell proved that this hidden variable that would save locality, would make sense, don't exist. And if they don't exist, then it means the world is non-local. That's a proof of non-locality. Most physicists don't put the two together. They don't understand EPR as a result of stating Bell is a no hidden variable theorem, and then people say, oh, but we knew that hidden variables don't exist, and von Neumann proved it, and so on. It's a maximal confusion. You just have to put these two simple arguments together. Most physicists, even very clever ones, don't do that. Gell-Mann, for example, or Hawking, I don't want to give name, but lots of them. Born did not understand EPR, and God knows what. These geniuses did not understand these simple arguments. Very strange. Yeah, it's what I call it the rational completion of quantum mechanics. Because, you see, in the end of the day, if I say to a physicist, here is an electron here outside of your laboratory, and it has such and such wave function. I give you the exact wave function, the spin, everything. What does it mean? what does it mean? It means that if I take this electron, bring it into a laboratory and measure and do some so-called measurements with it, then I get such and such result with such and such probabilities. That's what it means. Okay, but if somebody in an astronomer say this planet will be at that place in 6 months, okay, in the sky, it doesn't mean that if I look at it's important about the meaning. It doesn't mean that if I look at the planet with a telescope, then I will see it at such a place in 6 months. That's true also with additional hypotheses, namely that the sky is clear, that my eyes function, the telescope works as advertised, etc. But it doesn't mean that I will see it. It means that the planet will be there. And if you don't know what it means to say the planet will be there, then you don't know English or French or whatever. So that's what the meaning. The problem is that my problem with quantum mechanics, I've written many times that the problem is not the reduction of the wave packet, but it's the meaning. What does the wave function mean outside of laboratories? If it doesn't mean anything outside of laboratories, then you have given up the goal of physics. You may say we are forced to, don't have anything better to do, and that's what more or less what Bohr thought. But it seems to me, first of all, it's a sort of a disaster. Okay, why do physicists celebrate the end of physics as if it was a great, major advance? And that would mean we can't speak about the world. Period. We just speak about what happens in this little operation in the laboratory. But then why do we build laboratories? We go to a government and say I need $1 billion to build a laboratory. And then I say, because I'm going to discover the laws of nature and the ultimate laws of nature, etc. And then in private, you say, no, there are no laws of nature. We're just doing a little experiment to amuse ourselves. But, and then we, of course, it world goes outside of the philosophy seminar and the government say, what do you mean? You're just amusing yourself. I mean, and then there's an ethical problem there. It seemed to me that, of course, if Bohm didn't exist, if the Boyle Bohm didn't exist, then I don't know what I would think. But it seems to me that it gives the simplest possible completion of quantum mechanics, and in the most vexing sense for the people who have claimed that it's impossible, because it says that matter moves. I mean, as my friend Detlef used to say, I mean, it means that, particles actually move. And for example, in the double slit experiment, the particle goes through one slit, the wave goes through both slits, and because if both slits are open, and then of course that wave influences, guides the motion of the particle in a different way than it would if there was only one slit open. What could be more natural? And you can do that with the delayed choice experiment, you can do with all experiments. You just have a very simple explanation in terms of matter in motion, matter guided by a wave. And the wave function now has a physical meaning outside of laboratory, like the electromagnetic wave. It's weird because it's defined on multidimensional space, but nevertheless, it just, guides the motion of particles. So what could be more simple? I mean, it's just shocking that you say, no, particles actually do have position, and they have position at all times, and they have trajectories, therefore have velocity at all times. Totally contrary to the dogma. But if you try to measure the velocity, so-called measure the velocity, then of course you have to set up an experiment, and then you can show that what you're going to measure is not the real velocity, but something which coincides with the prediction of quantum mechanics. To explain it concretely, take a particle in the ground state in a box. Then, of course, that's a wave function which is real, which according to Bohm's guiding equation means that the particle is at rest. So its velocity, we know it, is zero. But if we want to measure it, how do? You can't just look like if you were God and look at the particle somewhere, where the particle is. So you have to remove the walls of the box. And then by doing that, the particle starts moving, and it moves in certain ways so that if you measure the distance traveled after a certain time and divide by the time that has elapsed, then of course you get a velocity, and that velocity is random depending on the initial position of the particle, and is distributed according to the absolute value square of the Fourier transform of the wave function, of the initial wave function. So it's in agreement with quantum mechanics, and do the calculation. It's in my book. It's not original, and it just follows from Bohm's equation.